Okay, so the topic is problems on efficiency of a transformer. In the previous class we have learnt about the major losses occurring in a transformer are core losses and copper losses. And we have seen the efficiency of a transformer. The efficiency is output power by output power plus losses. If we require the percentage efficiency, that is multiplied with 100, and that can also be given as output in terms of V2 I2 cos pi by V2 I2 cos pi plus double naught plus I2 square R naught 2 into 100, where double naught is core loss and I2 square R naught 2 is copper loss. We also see the maximum efficiency and the condition for maximum efficiency of a transformer, and also kVA corresponding to maximum efficiency. This was the thing. And now the solution for this is full load secondary current is equals to 5 into 10 power 3 by 440 is equals to 11.36 amps. And from AC test, let's see WSC of 25 watts. We know that WSC is equals to ISC square R naught 2, and R naught 2 is equals to WSC by ISC square, which is 25 by 6 square, which gives 0.695 ohms. And we know that Z naught 2 is equals to VSC by ISC, that is equals to 10 by 6 is equals to 1.67 ohms. And from that we can find X naught 2 is equals to under root Z naught 2 square minus R naught 2 square. From that X naught 2 is equals to under root Z naught 2 square minus R naught 2 square, which gives us under root 1.67 square minus 0.695 square. From that we get the answer 1.519 ohms. The full load power output is equals to VA rating into power factor, nothing but VA rating into cos pi. So VA rating is 5 into 10 power 3 into 0.8. That gives us 4000 watts. The full load copper loss is the WC is equals to 11.36 by 6 into 11.36 by 6 square into 25. That gives us 89.62 watts. And from constant iron losses from OC test, we can note that W naught is equals to 70 watts. And from that the power input is equals to output plus losses, that is equals to output plus the losses are divided into 2 WC plus WO, and we have the total data output of 4000 and WC of 89.62, and W naught is given from no load test, that is 70, and the total is 4159.62 watts. And the percentage efficiency is equals to output power by input power into 100, that is equals to 4000 by 4159.62 into 100. That gives you 96.16%. So the efficiency of the transformer is finally 96.16%. Okay. And the secondary terminal voltage, that is V2, is equal to E2 minus I2 Z02. That gives you the Z02 of R02 plus JX02, that is over here, of 0.695 plus J 1.519 ohm, which is converted into polar form as 1.67 at an angle of 65.4 degrees ohm. And cos pi 2 is equal to 0.8. From that, the pi 2 is equal to cos inverse of 0.8, which is of 36.86 degrees. And whereas I2 is equal to 11.63 at an angle of 36.86 degrees, measured in amps. And from that, V2 is equals to E2 minus I2 Z02 is equals to 440 at an angle of 0 minus 0 degrees minus 11.36 at an angle of 36.86 degrees into 1.67 at an angle of 65.4 degrees. From that, E2 is 440 plus J0 minus I2 is 1 second, already E2 and I2 has been mentioned. So from this, the result is 440 plus J0 minus 18.97 at an angle of 102.26 degrees, which is again given as 440 plus J0 plus 4.028 minus J 18.53. That in terms again into 444.028 minus J 18.53 is equals to 444.4 at an angle of minus 2.39 degrees volt. And please make the note of all these problems when I am just explaining you. And we'll see the example 2. A 50 kVA 4600 by 230 volts 50 Hz single phase transformer gave the following test results. The OC test of 230 volts 285 watts on LV side, and SC test 150 volts 10.87 amps 615 watts on HV side. Calculate the percent efficiency when the load is number 1 rated kVA at a power factor of 0.84 power factor lagging, and B 6 by 5 times rated kVA at a power factor of 0.86 lag. Please make a note of this question. Take 2 minutes of time, read the question properly and try to solve it. Just note down the question, read it twice, analyze it, make the given data, required data separately, try to solve the problem. If that won't happen, then I'll show you how to solve it. Okay, let us move into the problem. Already I have just given you 2 minutes. And now the given data of this is VA rating is equals to 50 kVA, that is equals to 50 into 10 power 3 VA. E1 is equals to 4600 volts, E2 is equals to 230 volts, and frequency F is equals to 50 Hertz. Okay, and from that double naught is equals to 285 watts, WSC is equal to 615 volts, ISC is equals to 1087 amps, and the required data is efficiency is equal to question mark at rated kVA and at 0.84 lag, and also the efficiency at 6 by 5th kVA and at 0.86 lag. Just make a note of this. And moving to the solution, we have full load primary current I1 from the kVA rating is equals to 15 to 10 power 3 by 4600, which is E1, that gives you 10.87 amps. And from that the full load power output is equals to VA rating into power factor, nothing but VA rating into cos pi, that gives you 50 into 10 power 3 into 0.84. The total is 42,000 watts. And from full load copper losses from SC test, the copper loss is given by 615 watts from the given data, and the constant iron losses from OC test is double naught of 285 watts. Please make a note of that. Okay, now the power input is equals to output plus losses, and the output plus WC plus double naught. The problems are same as in the previous, and the output is 42,000 plus WC is 615 plus double naught is 285. And the total is 42,900 watts. You simultaneously please make a note of all these things. This is the total power input, and from that the efficiency is output power by input power into 100, which gives you 42,000 by 42,900 into 100. that gets 97.9%. See here, you can observe from each and every problem that the efficiency of a transformer is above 90 and 95 only. Since I have said you in the starting classes that efficiency of a transformer is high than any other devices like DC motor, generator, or AC motor or AC generator. Since it has only two losses, that copper and iron. So the highest efficiency getting device in this world is only a transformer. So please make a note of this. Now the second one is 6 by 5 times rated kVA power output is equals to 6 by 5 into VA rating into power factor. That is 6 by 5 into VA rating into cos pi. The 6 by 5 VA rating is 15 to 10 power 3. You can observe that here. In the first case, he asked the full load. So the VA rating will be into 1 since it is full load. And now it is 6 by 5th time the rated kVA. So we need to just multiply with 6 by 5. Are you getting? Okay, so 6 by 5 simply you need to multiply for VA rating, that is 50 into 10 power 3 into cos pi of 0.86, and that the total is 51,600 watts. This is a power output. And the same we need to do for the copper losses too, because the iron losses may not change for any kind of load since they are constant losses, but whereas the copper losses are variable, so it changes from full load to no load, no load to full load. So the copper losses also has to be noted for 6 by 5 times the rated kVA load for copper loss. That gives you WCU is equals to 6 by 5 square into full load copper loss. That gets you W copper loss is equal to 6 by 5 square into 615 watts. That gets you 885.6 watts. Is that clear? So for the 6 by 5th times the output power is 5160, and for 6 by 5 times the copper loss is 885.6 watts, and the iron losses remain same for any kind of load. That to be noted. See the constant iron losses from OC test, which is of W0 is equals to 285 watts. Since it is constant losses, we are not multiplying with any of the factor. So the power input is equals to output plus losses, that is equal to output plus WCU plus W0. That is 51,600 plus WCU is 885.6, which was done in the previous slide, and W0 is 285, and the total 52,770.6 watts. This is the input. We have output and also the input for 6 by 5th load, and we can find the efficiency easily. See the percentage efficiency is equal to output power by input into 100, that is 51600 by 52770.6 into 100. We get 97.78%. Just make a note of this. Just take for 2 minutes. Once again, you just please analyze the problem and compare from the first to the first problem to the second. Get some idea so that you can solve the further problems. Is that fine? If it is fine, we'll move on to the next problem. Example 3. The efficiency of a 500 kVA transformer is 98% when delivering full load at 0.8 power factor and 98.5% at half load and 0.9 power factor. To calculate the iron loss and full load copper loss. In the previous case, he just asked us to find the efficiency of the transformer at some particular loads by giving iron loss and copper loss, and in this he is asking us to find the iron loss and copper loss by giving the efficiency at two conditions: at full load with 0.8 power factor at 98% and half load with 0.9 power factor with 98.5%. Just read the question and make a note of that. Write the given data and required data separately and try to solve the problem by your own. Okay. The given data is kVA rating is 500 kVA and he said us to find the efficiency at full load. Not to find, he just given us efficiency at full load and at 0.8 power factor of 98% and efficiency at half full load at 0.9 power factor, this is 0.9 PF with 98.5%. And the required data is W0 is equals to question mark and WCU at full load is equals to question mark. This is a clear cut of given data and required data. Please make a note of that. Okay, now moving on to the solution, which is given that the full load power output is equal to kVA into power factor, that is equals to 400 kilowatts, This is a kVA rating, and the full load power output should be multiplied with power factor. That gets us 400 kW. The input power is equal to output by efficiency. This is the output, and in order to get input power we have the efficiency. So the input power can be determined by output power by efficiency, which is 400 K by 0.98. That gets you 408,163.3 watts. This is the input power, and from this we can easily calculate the total losses like input minus output. And we know the input power and the output power. That can be clearly obtained as 8,163.3 watts. And this shows us the total losses of iron and copper. See, it is showing us the two losses W0 plus WC of 8,163.3 watts. And let us take this as equation 1, since it is the condition 1. And the second condition, the efficiency is of 98.5% at half load and 0.9 power factor lag. So here the half load power output is equals to half into VA rating into power factor. In the previous problem we have seen that 6 by 5th load, so we have multiplied with 6 by 5 to the power, and for copper loss 6 by 5 square, and for power 6 by 5. So simply here half load, so we need to multiply it by 1 by 2 to VA rating into power factor, which is half into VA rating into cos pi, which is half into VA rating is 500 into K, that's about 10 power 3 into 0.9. That gets 22,25,000 watts. This is just only a power output, and you know that we have efficiency and the output, so we can easily find the input power. The input power is equal to output by efficiency, which is of 2,25,000 by 0.985. That gets you 2,28,426.4 watts. And the total losses is equals to input minus output. And that gets you the input minus output of 3,426.4 watts. And same, this also will be including both iron losses and copper losses. You can see here double naught. As I've said you, the copper losses are also should be calculated for half load, but why it is 4 over here, since if it is half for copper loss we need to do it square times. So by this 1 square is 1 and 2 square is 4. That's the reason the 4 was there in this place. So double naught plus WC by 4 is equal to 3,426.4 watts, and just make this as equation 2. And previously we have equation 1, and now we're solving the above equations 1 and 2. we get the iron losses and full load copper losses as W naught is equal to 1.847 kW and WCU is equal to 6.316 kW. We need to solve the equations 1 and 2. That's a simple algebra. Please try to solve it and confirm me the answers for the iron and copper losses. Solve the equations, both the equations, and you will be getting any one, and by substituting that in any of the either equations, you will be getting the other. Please try to solve, all of you, and confirm me the answers. So that finally we'll be getting iron loss and copper loss. And there is another example, and here we have the maximum efficiency of 100 kVA, 6600 by 250 volts, 50 Hz single phase transformer, occurs at half load and is 98% at unity power factor, and calculate the full load efficiency at 0.8 power factor lag. Read the question twice to analyze. Okay. The VA rating is 100 kVA, E1 is 6600 volts, E2 is 250 volts, and frequency is 50 Hz. And he just gave us the maximum efficiency 98% at half load at UPF, and by unity power factor, half loaded power output at UPF. So the half loaded power output at UPF is given by VA rating by 2 directly by half. If it is copper, we need to half square the power, just half. So VA rating by 2 into power factor, the VA rating is 100 into K by 2. Since it is UPF, so it's 1. So directly 50,000 watts. This is the power output. The power input same as output by efficiency, 50,000 by 0.98 gets you 51,020.4 watts. And here the total losses of W0 plus WCU is equals to input minus output, as we have seen in the previous cases. And that gets you 51020.4 minus 50,000 gets you 1020.4 watts. And here the thing different from the previous problems to this is, in the previous case it was full load efficiency and now it's maximum efficiency, and we need to find, I think that the condition for maximum efficiency is the iron losses is equals to copper loss. That means both the losses are same. So here you can see at maximum efficiency WCU is equals to W0. So W0 and WC is same, so that becomes the 2 double, so that 2 gets cross multiplied, it gets by 2, so 1020.4 by 2 gets you 510.2 watts. So the each loss iron and copper will be of 510.2 watts. So the power output at full load at 0.8 lag is equal to VA rating into power factor, that is 100 into K into 0.8. That gets you 80,000 watts. And the copper loss at full load, WCU is equals to 4 into 4CU. Since that was for half load, that should be done by 4. So now if it is for full load, we need to multiply by 4. Since that was for half load. So WCU is equal to 4 into WCU, that is equal to 4 into 510.2. That gets 2040.8 watts. That's for full load. So WC at half load is equal to WC at full load by that formula you have obtained that. The power output is equal to output plus losses, output plus WC plus W naught, and this is the thing, output WCU and W naught. That total is 82,551 watts. Then the efficiency is output by input into 100. We have clearly the output and input. That gets you 96.9%. Is that clear to you all? Please make a note of that and analyze the problem once again. As I've said you to make a note of the every slide continuously with me. And I'm also giving you some time to make a note of this. If it is done, we'll move to the next problem. Example 5. A 500 kVA single phase transformer has full load copper loss of 7.5 kW and iron loss of 2.5 kilowatts. Find the efficiency at half load at a power factor of 0.8 lag, and also find the maximum efficiency and the kVA load at which it occurs at unity power factor. The same cases for every problem. You can see VA rating 500 kVA, W naught 2.5 kW, WCU 7.5 kW. The power output at half load at 0.8 lag is half into 500, half into VA rating into power factor, the same as in the previous. The half into 500 into K into 0.8 gets 200 kilowatts. The copper losses at half load, as you know that it should be square of half into full load copper loss. That gets half square into WCU is equals to 7.5 by 4 is 1.875 kW. The power output input is equals to output plus losses. The losses are both copper and iron. The output is 200 plus 1.875 plus 2.5. That gets in a total of 204.375 kilowatts. This will be the input. And finally we have input in our hand and the losses and the output, so we can clearly find the efficiency of a transformer. See, finally the efficiency is output by input into 100, which gets 200 by 204.375 into 100. That gets you 97.85%. equation 1. And finally, KVA load corresponding to maximum efficiency is given by full load KVA into under root iron loss by full load copper loss. This is a new thing to you, just please make a note and just be cautious. The full load KVA is 500 and that should be in KVA and should not be into 10 power 3, the full load in KVA. If it is 500 kVA, just please mention it 500 only into under root of iron loss by full load copper loss. Iron loss is 2.5, the full load copper loss is 7.5. And the final answer is 288.68 kVA. This one is a new thing to you, so please be careful and make a note of this. And finally, the power output at UPF is VA rating at max efficiency into power factor. VA rating is 288.68 into K into 1. Since the power factor is unity, so it is 1. So the final power output is 288.68 kilowatts. Since the copper losses is equal to iron losses at maximum efficiency, the WC is equal to W naught is equal to 2.5 kW. And in a total loss of WC plus W naught, which is of into 2, so that in a total of 2 into 2.5 gets 5 kilowatts. So now the power input is equal to output plus losses. The output is 288.68 plus 5 is the total loss, gets you 293.68, and the efficiency for maximum is output power by input at maximum conditions. That is 288.68 by 293.68 into 100 gets you 98.3%. Just be careful with these problems with the conditions like maximum efficiency and half load or 6 by 5th load or 3 by 4th load or 1 by 4th load. You need to cross check them 1 to twice and try to solve the problems. So this is the thing of about the problems on efficiency of a transformer. And the summary is, the efficiency formula, output by input into 100, the condition for which maximum efficiency occurs when variable loss is equal to constant loss, nothing but WC is equals to WI. And I'm giving you some problems to solve by your own, which have been kept with frequently asked questions. Let's say problem number 1. And problem number 2. I have mentioned the answers also so that you can solve and cross-check the answers to it. And the problem number 3, just read the question carefully 1 to twice and make the answer and cross-check the answers which I have given you. There is a problem number 4.